last lap for today's presentations. We're going to have 3 presentations, one a bit longer than the other 2, and then we're going to have a sort of general panel discussion at the end, where we'll try and mop up as many questions as we can that have been asked that might not have been answered yet. So without any further ado, I'd like to introduce our first speaker of the afternoon, who is a colleague of mine. It's Neil Meyer. Neil Meyer is a professional civil engineer with over 22 years experience in the water field, of which about 21 is with the company WRP Consulting. Neil is an executive manager of water loss management at WRP and has been involved in numerous water loss reduction projects, both in South Africa as well as in many other countries around the world, including Rwanda, Australia, Zimbabwe, the Philippines, and I'm sure the one that he won't forget is India. He joined me on a project in India once, which was quite an eye-opener. Just on that point, 90% or more of India's cities operate on intermittent water supply, which means once you're on to intermittent water supply, it's not a good thing, as we will discuss tomorrow, but 90%, over 90% of cities in India operate on intermittent water supply. So South Africa really, we've got problems, but we're not there yet. So we can still turn this round if everybody starts doing the right thing within the municipalities. Neil has designed and commissioned some of the largest advanced pressure control installations in the world. He's a specialist in pressure management. He designed and commissioned the massive Mandalay installation, which is in Cape Town, which supplies, I think it's around 80,000 connections and about 500,000 people with water. It's a very large installation and it's operated using advanced pressure control. And Neil designed that and commissioned it. He's also designed and commissioned probably 100 or 200 smaller pressure reducing valve installations and carried out some fairly major projects on pressure management, which hopefully he'll touch on in his presentation. He's organized and presented at most of the IWA water loss events, and he assists me in any of the summits and conferences that we organize. So Neil's been heavily involved in all of that. And another important thing he's done is he's developed a hands-on course on pressure reducing valves, a 3-day course to show people how to use excuse me, pressure reducing valves and fix them, etc. So that's another very popular course that he does. So Neil, I would like to hand over to you, if I may, if you can get your presentation up and running. And we're giving you about an hour, I think, if that's right. Yep, you've got about an hour, and we look forward to hearing what you're going to say. Thank you, Neil.
Okay, thank you, Ronnie, for that introduction. So as Ronnie mentioned, I'll be sort of discussing pressure management and providing, sort of an overview of different aspects of pressure management. Ronnie has mentioned, he's shown this slide sort of earlier, and it's sort of the different arrows impacting sort of on loss reduction, and one of those is pressure management. So that's the one that I'll be talking on in this presentation, the pressure reduction. So it's a topic and an aspect that we are quite passionate about, and we see pressure management as one of the sort of the low-hanging fruit in water loss reduction. So if it is possible to reduce pressure in a system, then you should be able to achieve significant savings from that pressure management. Having said that, we realize that pressure management will not work in every single system. Ronnie mentioned just now the example of India, and I can recall when Ronnie invited me sort of to that training course sort of many years ago. I did a presentation as I'm doing now, and I went on about the benefits of pressure management, and that you should do pressure management to save water. And then after the training course, one of the gentlemen raised their hand and said, "But how are they supposed to reduce pressure if there is no water?" So I had to acknowledge that there's pressure management as you cannot implement pressure management in every single area. But where possible to implement pressure management, that's certainly one of the low-hanging fruit that should be considered. So the concept of pressure management is quite simple to understand, that if there is leakage in a system and the system operates and the pressure is lower, the leakage will be lower. As we see in this slide, there is a crack in the pipe and there's water coming out, but it's under very low pressure. If you increase the pressure on that very same pipe, and the leak is still the same size, but now the leakage through that crack is now significantly higher, and it's just the pressure that's driving the leakage on the system. So the reverse of that is, if you are able to reduce the pressure in parts of your system, then you should also be able to reduce the leakage, as we've seen now in these two photographs. So what we've noticed in some municipalities is that as a sort of pressure reduction tool, some municipalities use an isolating valve, where they throttle the valve in an effort to reduce the pressure in parts of the network. So we note here on the screen, it's relatively cheap to install a valve. In many cases, there are already valves on the system. But the problem is that isolating valves they're not made for the purpose of throttling. So the valve is not going to last long if you use it for throttling, and you cannot regulate the pressure. So if you throttle the valve, you don't have control of what the pressure would be in that evening, once the flows has gone down. So it's really not an ideal tool to use for pressure management. In this photo on the next slide, we can see a gate valve that was used for throttling, and eventually the cavitation just sort of ate a hole right through the body of that gate valve. So it's not an ideal option for pressure management. So what we rather use for pressure management is a pressure reducing valve. So this is a schematic of one where the high pressure comes in on this left-hand side of the valve, and then the pressure reducing valve lowers it to a lower pressure. So, and regardless of the flow rate, whether it's high or low, and regardless of changes in the upstream pressure, if the PRV works correctly, it will give us a fixed pressure on the outlet of the PRV. So that's what we want for pressure management. We don't want a throttled gate valve that will give us a varying pressure depending on what the flow rate will be. We want a fixed outlet pressure regardless of flow, regardless of changes in the upstream pressure. So if we zoom in a bit more to a sort of to the inside of a PRV, so this is how a PRV will look like if you cut it in half. So this large valve here is the PRV, and on top of it, this smaller valve here, sorry, this valve is the pilot valve. So you set the PRV by adjusting the pilot valve. And once you go into it, you see it's actually a fairly simple operation where you balance water pressure against the spring tension in the pilot valve, and that's how you set the PRV. You basically you balance water pressure against spring tension. So it's not an overly complicated system. That you've got hundreds of different parts and moving parts, so it's a bit more complicated than a normal gate valve, but you don't have hundreds of moving parts here. There's a few parts, a few springs and a few rubbers, so it's not too difficult to understand, but the basic concept is equalizing water pressure against spring tension. So there's lots of different companies that sell PRVs. I know Ronnie likes to talk about the green, the red, and the blue PRVs. There are many companies that sell PRVs, also in South Africa. So normally when we get asked the question is what type of PRV should be used, it's very similar to the answer that Stuart gave earlier on the leak detection equipment. And it's basically, it does not really make a big difference which company a valve sort of you use, as long as it's one of the recognized companies, and as long as you're going to get backup service from that company where you bought the valve. I mean, you should be able to come right with using any of the large sort of known companies. So the next few slides, we'll look at different pressure management options. So the first one is going to be a fixed outlet PRV, where there's just that pilot valve, which I've just shown on the previous slide. The next one is then a time controller on the PRV. The third one is a flow controller on the PRV. And the fourth one is a sort of a closed loop or an intelligent sort of controller. So we'll go through the options. So the fixed outlet PRV, the first option, the PRV is set to a fixed pressure, as we've seen on that previous slide. If you install a data logger on a fixed PRV, you should see more or less a straight line coming if you log the pressure on the downstream of a PRV. So it's a fixed pressure at the outlet of the PRV. It's fairly simple sort of to set up and to maintain, but you must set it at sort of peak demand periods. Because the PRV cannot change the outlet pressure, you need to set the outlet pressure basically for the worst case scenario, when the pressure in the critical point of the network is going to be lowest. So if you use pressure management with a fixed outlet PRV, we've seen many examples where significant savings can be achieved. So this is an example from Johannesburg. So on the left hand of the graph is the PRV downstream pressure, the purple line, and the blue line is the flow. Before a PRV was set and commissioned. And then on the right hand side of the screen is the same PRV, but at a lower PRV setting. And one can see just by lowering the setting from there to there, the significant impact that made on the flow going into the zone. And the main reason for that is leakage is driven by pressure. So if you are able to reduce the pressure in the system, you will reduce the leakage. And if you reduce the leakage, you reduce the total input of flow into that system. And that's what we're seeing on this graph. So this is a schematic of how a fixed outlet PRV in the network will work. So the PRV is on the inlet of the zone, and on the far end of the zone, the critical point of the zone, you are going to get some pressure variance because you've got some pressure head loss through the zone from the point where it gets into the zone at the PRV, traveling through the zone up to the critical point. So you will get some variance in pressure. Obviously, that will vary from zone to zone, depending on the size of the reticulation. But normally, you're going to get some variance at your critical point. So this schematic then shows the same, and it shows that the PRV, in this case, is set at 60 meters of water pressure. And because of the pressure loss through the system, the pressure that ends up in the middle of the day or at the peak hour at the critical point is about 20 meters. So in this example, the PRV you have to set the PRV high enough that you get the pressure of 20 meters at the furthest end or the highest point of your zone. At night, the pressure in that zone is going to increase as people use less water. There's less flow and then less friction, so the pressure is going to build up in your zone. So that tells us if there is a way to reduce the pressure at night further than the pressure during the day, one should be able to achieve additional water savings. And this is where advanced pressure controllers come in. So the pressure controller is installed on the PRV, and it allows you to, during off-peak periods, to further reduce the pressure. So the first example of a controller is the time controller. So it provides a fixed time variable. So you literally set the controller to at a certain time in the evening to lower the PRV outlet pressure to a certain level, and then the next morning to increase it back sort of to the same level. So every day and every evening it will switch between the higher and the lower pressure. So by doing that, you remove some of the excess pressure at night, and then you are able to achieve additional water savings compared to a fixed outlet PRV. The schematic for the time controller looks then slightly different to what we've seen previously from the fixed outlet PRV. Because we are now reducing the pressure at night with the time controller, we are now able to achieve slightly less variance in pressure at the critical point, because we are taking out some of that excess pressure by reducing the pressure at night at the PRV. So, and by reducing the pressure at night, we are achieving additional water savings. So this is a graph showing a time controller on a PRV. So during the day, the pressure on the outlet PRV is slightly higher, and then during the night, the pressure is reduced. And then it goes on every day, and every evening it goes slightly up and slightly down, depending on the settings and the times that controller will go up and down. And by reducing the pressure at night, one is able to reduce the leakage further in that zone. The next type of controller we'll discuss is the flow modulated controller. So in a flow modulated controller, the controller modulates the PRV outlet pressure depending on the flow that goes through that PRV installation. So the higher the flow, the higher the pressure. And the lower the flow, the lower the pressure. And the reasoning is that during the peak hours, when the flow is higher, there would be a requirement for higher pressure. And in off-peak periods and at night, when the flow is lower, there would also be a lower pressure requirement in the zone. So by using a flow modulated controller, one is normally able to get a straighter line of pressure at your critical point, not exactly a straight line, but a straighter line than some of the other controllers. And if you set it up correctly, you can achieve higher water savings than with a fixed outlet controller. But the flow modulated controller does come with at a higher cost, and it is more difficult to set up, and there's more that can go wrong that you need to monitor in that zone. For example, if there is a very large burst in that zone, the flow would go up because of the burst. And if the flow goes up, the flow controller would not be able to differentiate, why the flow goes up. So the controller would push up the pressure when there's a burst in the zone. So those type of things would need to be monitored, and you in those type of zones, it's probably best to put in 24/7 monitoring, so that you can pick up if there is a burst in the zone and attend to that as quickly as possible. So this is then the same schematic as that we've seen for the previous examples. And in this case, because the PRV outlet pressure is now varying between, according to the flow rate, you are able to achieve a straighter line at the critical point. So not exactly straight, the schematic is maybe a bit misleading, but you are able to remove more of the excess pressure in that zone. And then the last type of control is sort of the advanced or the closed loop or the intelligent controllers. And for these controllers, there is a pressure logger that's installed inside and at the critical point of the zone. And that critical point logger continuously monitors what is the pressure inside the zone. And then it sends that information back to the controller, and the controller then adjusts the pressure in the zone according to the information received from the critical point. So, it's quite an advanced controller. So again, if you are able to set this up correctly, you should be able to achieve significant water savings. But it also does come at an additional cost. And there are now more factors to take into account. So, for example, the communication between the critical point logger and the controller. You need to consider what happens if that communication is not there anymore. So there's a bit more that can go wrong sort of with this controller also than some of the previous options. So we would consider this controller maybe in certain zones where maybe significant additional water savings can be achieved compared to some of the previous methods shown. There are also hydraulic solutions to flow control. So this is an example of some of the control valve companies that also have valves that can do flow modulation, but not using any electronics. It's all hydraulic. So the valve gets set up so that also the outlet pressure of this PRV is going to be higher at higher flow, and it's going to be lower at lower flow. So again, in the concept, sounds quite promising, but one can, by looking at these valves, one can see that some of them looks like it can potentially be fairly complicated sort of to set them up. So if you are considering to use this, you would need to make sure that you've got sufficiently trained people that are able to set up and maintain these valves. Can I maybe ask the IT people, is it possible to put the poll questions on the screen right now, or would it work better if it comes? Oh, well, that was quick. Okay. So we normally do a sort of a PRV course, as Ronnie has mentioned. and then we take the delegates through the different aspects of how a PRV works. So I was thinking, I mean, since we were asked to ask some questions, I thought I'll throw in a few PRV questions. So if you're not a PRV question, maybe you don't need to answer it, but otherwise you can maybe just take a guess. But these are some of the questions that we will sort of ask delegates if we do a PRV course. Then we at the end of the course we give the delegates a test, and then we see if they understand how the PRV works and sort of all the different aspects. So if you don't mind, if you're able to sort of go through these poll questions and sort of put in your answer, and just for interest's sake, want to see what are the results we are getting. Maybe the IT team can advise me, is it possible to see the results immediately now, or do we have to wait a bit before we can see the results?
Neil, you can see them immediately once you tell the back office that you're closing the poll. So give your delegates a few seconds, 30 seconds, and we'll close the poll and you can have the results immediately.
Okay, thank you. Okay, excellent. So thanks for that clarification. So if everyone can fire away there at the options on your screen, and then we'll give it a few more moments, and then we'll put the results on the screen. So while you're busy with that, I'll maybe just show I've got a few photos showing these PRV courses. So we show the people how to take a PRV apart. So this is a course that was done at Fennel Road Depot at Johannesburg. So the delegates get a chance to take the valve apart and to build a hydraulic control circuit on a PRV. And then we've asked a PRV contractor to build us a training rig. So it's quite a heavy thing. So you literally had to build a custom trailer, and then on the back of that trailer we've got this pipe circuit, and on that pipe circuit we then have a PRV. So while the water is flowing through the circuit, the delegates sort of get a chance to service the PRV, and then we give them a troubleshooting session on that same rig. So we ask them to look away for a moment, and then we break something on the PRV, but we don't tell them which component, and then we ask the delegates to find sort of the missing or the broken sort of component. So we find it's a good way to teach the operational staff how to work on a PRV, but without actually damaging sort of the water network. So maybe is the IT people that poll, is it possible to put the results now on the screen? All right, okay. So just for interest's sake, we can maybe quickly sort of scan through these ones. So right, okay, I've got the results on the screen. So what's the purpose of the spring inside the PRV? So not the spring in the pilot valve. So that's quite good. I mean, we've got 71% people with the correct answer. So it's to assist the PRV to overcome potentially balanced forces. So that's wonderful. So we've got definitely a very sort of educated sort of a crowd here. So that's great. So if the downstream pressure of a PRV is higher than the upstream pressure, what should be checked for? So more than half got that right. So that's good. It's sort of, it could be better, but at least that's promising. So, and it's the zone cross-boundary connections. So we always tell the delegates that if the downstream pressure of a PRV is higher than the upstream pressure, they should leave the PRV alone. The pressure is coming from somewhere else, and it's coming from a cross-boundary connection. And then the last question, I only realized after I sent the question that it was a bit of a unintended trick question. And it's so that one is my fault. So, but the question is, if a PRV is not able to close, which item should be checked for? And if one would look sort of carefully through those items, the second item is definitely one of the options, but actually number 3 and number 4 are also options. So on that one, there's the multiple question didn't work didn't work that well. So thanks for everyone. I think that was just for instance sake, just to break the discussion for a bit. The next few slides that I'll talk about is some of the large PRV installations that we've looked at. So we quite liked the large PRV installations. So it's an impressive installation to look at, and the water savings achieved there is quite significant. Again, we realize that you cannot do a large PRV installations in every municipality because it's dependent on the network. But where possible, it makes for quite a sort of an interesting project. So the first photo is just a photo I've pulled off the internet of a very large PRV. So this one is a 600 millimeter PRV. And in the next few slides, I'll show you that so some of the large PRV installations that we've done, we've not gone for the largest diameter PRV that we've put in. So we've rather gone for smaller diameters that makes it sort of a bit easier to procure and maintain those PRVs on the long run. So the first one I'll show is the Kailicha advanced pressure management installation. So this one is the oldest. It's now just over 20 years old. So this was the first sort of large PRV installation of its kind, as far as we know, maybe in the world, in the city of Cape Town. So there one can see basically the three legs sort of in this PRV installation, where each leg has got a strainer and a water meter and a PRV, as opposed to that previous slide that I've shown with a very large sort of diameter PRV. The savings achieved on this Kailicha installation was enormous. I mean, it resulted in water savings of 9 million cubic meters per annum. So that was, an incredible sort of water saving for one project. Cape Town is also busy with a new PRV installation. So Kailicha has developed over the years, and the demand has also grown. So Kailicha is now getting a new bulk supply from the eastern side of Kailicha. So with that new bulk supply, there was also a need to install a PRV on the new bulk supply. So we've assisted with the mechanical design, and Ingerop is doing the structural and the implementation of that PRV, and that installation is currently under construction, and they hope to commission that one now in the next few months. The next large PRV installation is also in Cape Town, so that was in Mitchell's Plain. So there's a photo of the Mitchell's Plain installation, very similar sort of to the previous ones. And the third large PRV installation is in Sebokeng, Everton. So there's a photo of the Sebokeng Everton PRV installation. And again, a few photos of the construction process. So there's the pipe before the PRV was installed. And there's the complete PRV installation that was cut in on one day. So there was a requirement from the municipality that the water supply to Sebokeng and Everton had to be back online within a very short period. So between the team that designed the PRV and the contractor, they basically came up with a plan of basically constructing the whole PRV installation on the side of the installation, and then once the water was cut or the water pipes were cut into, that complete insulation, as you see there, was sort of lowered in place. And the water was back on, I think Ronnie can confirm, but in sort of less than 8 hours from start to the point that water was back on. So the Sebokeng installation also achieved significant water saving, so 8.5 million cubic meters per annum. So it shows that if it is possible to install a large PRV installation, the savings that you are able to achieve with those installations can be astronomical. So in the case of Sebokeng, it's approximately 2 Olympic-sized swimming pools every 2 hours. So 2,800 cubic meters of water night flow. And then, sorry, just moved in the wrong direction. And then for the same Sebokeng project, we also monitored the impact of that project against the Rand water input volume for that area. So one can see the baseline is basically this blue line, and the green is the Rand water meter reading, the Rand water monthly volumes. And one can see once that pressure management project was implemented, there was a notable reduction sort of below the baseline going into that area. So in summary, the large PRV installations, we were able to achieve significant water savings. And then the last 2 slides that I'll show is just something on PRV security. So we've seen over the years that it is unfortunate that in many cases, after lots of effort was done to get a PRV installation to look really good, and you've maybe installed electronic equipment to monitor and to control the pressure. If you then get vandalism and theft in that same installation, it can put the municipalities plan to reduce water back significantly. So where possible, we try to encourage municipalities. They need to secure PRV chambers, because it's very easy to vandalize a PRV chamber if you are able to get inside. So there are a number of solutions. I mean, the one on the screen is sort of is quite an advanced one. This is a company that sells a very high quality lockable cover. And one can just see from that photo on the right, the reinforcing that goes into this chamber. I mean, it's sort of, it's pretty much a bomb-proof chamber. So if you've got chambers where you just cannot control the vandalism, there are options sort of available. But then lastly, just a funny slide I want to show. If maybe you've got some budget constraints to secure your PRV chambers, you can also maybe consider some cheaper alternatives. So when we did a project in Johannesburg, we logged all their PRVs, and we came across one PRV that had this snake in it. So with great effort, we arranged with a snake handler sort of to remove the snake so that our staff was able to get inside. And we equipped the PRV with a new pilot valve, and we installed the data logger. And a week after that, everything was stolen. And then I realized that there was a reason why that snake is in the chamber. So I sort of laughingly now sort of look back at it, and I think, maybe there's some merit in that, but only for municipalities that are able to sort of to handle the snakes in the chamber. So thank you all. I'll leave it then. That's the end of the presentation. Thank you.
Okay, thank you, Neil. I think that was very interesting. We've got some questions coming up on the screen there just now, and maybe just while we're getting some of the questions from the delegates, what would you say if you look at if you look at the different options, time control, flow control, advanced pressure control, or just normal bog standard fixed outlet control. Where would you say the percentage savings are in general from the sort of 200 installations that you've designed over your 20 years in this field? Is it 50-50 or 80-20 or 90? Just roughly, what sort of additional savings do you think you can get? I suppose it might depend on area to area.
Yep, certainly, Ronnie. It does depend from area to area. If I must just pick a number, out of the air, I would probably guess 80% of the savings, maybe between 70 and 80% of the savings you get from your fixed outlet PRV, and then sort of the remaining bit you can get from the advanced pressure controllers. But as you've noted, it will vary from one municipality to the next and one zone sort of to the next. I think for us, if we evaluate whether we want to install a pressure controller, we look at the potential additional water savings. And if that additional water savings quite significantly outweighs the cost of the controller and the extra maintenance, then it makes sense. But if the additional cost and maintenance of a controller does not really significantly outweigh the cost, then we would recommend keep it at a fixed outlet PRV.
Okay, thanks, Neil. I've got a question here from Chabedi. What is the impact of the wrong size of PRV? So if you're putting in a PRV and you put in the wrong size of the PRV, what is the impact of that? I suppose it's on your wallet as well as your system.
Yeah, it's a good question, Chabedi, and I think in our experience, and maybe it differs from one municipality to the next, but in our experience, most of the PRVs that we encounter in water networks tend to be oversized. So they are too big, in some cases much too big for the flows that sort of they need to operate on. A PRV can handle quite a big range in flow, so it's normally not a big problem. But if it gets extreme and the PRV is significantly oversized, so number one, as Ronnie mentioned, then it means the cost of the valve was unnecessarily high. But then secondly, what you could pick up is the PRV is not able to handle the flows at night very well. So there's a term that they talk about hunting. So the opening in the PRV gets so small in the evenings that for one moment the PRV closes and the next moment it opens, and it opens, closes, and you get that hunting effect. So certainly the PRV sizing is something that needs to be carefully looked at when you install a PRV. And in our experience, what we see is that many PRVs are actually oversized. And I think the reason for that is, there are many times uncertainties. You don't exactly know what the flows will be or what the fire flow requirement will be. So if you do your calculations and you work out at a certain size, you maybe want to just increase a little bit, to cover for those uncertainties. But in doing so, you could in some cases end up putting in a valve that's actually too big for the flows that needs to be handled.
Okay, thank you, Neil. We've got a question from Nathaniel Padiachi. We are interested in installing flow control valves on some bulk water pipelines. Since pressures and flows are interrelated, how different are flow control valves from pressure reducing valves? In other words, is a flow control valve not just a pressure control valve that is flow modulated? I have heard that maintenance is high, not just setting up. We want to install on our bulk lines and not the reticulation. and just want to allow a certain volume through per day at each point. We don't want to empty the lines as it induces entrapment of air. Obviously, that would cause a lot of damage. And that is why we are looking at flow control valves as opposed to just shutting off after the daily quota has passed. So what I think the guts of this question is that at the moment, they are looking at introducing intermittent supply to make sure that they only get a certain volume into an area each day. And what they're now looking at, which is obviously what we've been shouting about and that we'll talk about tomorrow, is that controlling the flow, i.e. the pressure, I suppose, in order not to cut off the area. I don't know if that's, I don't know, Neil, if I've given you a real woolly question there or not. Can you add anything on that?
No, that's fine, thank you. So to answer that question, there are similarities sort of between those sort of options mentioned, and it's more got to do with exactly how it works. So a flow control valve or a rate of flow control valve will have a rate of flow pilot valve, and a pressure reducing valve will have a pressure reducing pilot valve. So in a case of a rate of flow valve, you would set the rate of flow pilot valve to allow for a maximum flow rate. So, pick any number, sort of 50, sort of liters per second or whatever the flow rate is that you require. If the PRV then reaches that flow rate, it would basically start sort of to throttle back, and it would not sort of allow the flow rate to go higher than that. And by throttling back will then result in the pressure also reducing downstream of that valve. So there are similarities sort of between those two. They are just slightly different setup. So in terms of that example, so if the aim is to avoid going on intermittent supply, then I definitely think it's any option should be considered before going on to intermittent supply. But maybe one should sort of carefully look at what the impact will be of going on to rate of flow control for that pipeline, because one can imagine that in the peak hour, the flow is going to be the highest. And if the flow is the highest, the rate of flow control valve is going to throttle back the most, which means the pressure is going to be lowest during your peak hour. So you need to carefully look at the system and see, is that the optimal solution for what you require in that zone? And is it not going to create significant problems in that area if the pressure is then so low in the peak hour?
Okay, thank you, Neil. We have a question here from Malondolosi, and the question is, of the 4 water loss strategies highlighted in the first presentation, which one is the most effective? That's a good question.
Okay, that's an easy one, and yeah, our view is and we've seen that in many examples that it is pressure management. So pressure management is the low-hanging fruit. So as we've mentioned, it's not possible to do pressure management in every system, due to various reasons. But where possible, we would recommend you look at pressure management. It's in all the examples that we've seen in the projects, you normally get very good payback periods. If you compare the cost of the installation, the design cost, the implementation cost versus the savings that you'll get, you normally get a relatively good payback period, which can vary from 3 months in some cases, if you've made lots of water savings, to maybe 2, maybe maximum 3 years. So we normally see a very good payback period on pressure management projects.
Okay, I think it's also, maybe I can just add a bit to that, add a bit of a caveat. That diagram with the 4 arrows, you should think of it as a balloon trying to expand. And if you keep the 4 arrows in check, then you keep that balloon in check. And the balloon is your leakage. And if you ignore any one of those 4 interventions, it will allow the balloon to expand in that direction, in which case your overall leakage may go up. Even although you've got pressure management under control, if you don't have some of the other things under control, such as leak detection and repair, if you ignore that completely, you may find that that becomes your dominant problem. Or if you don't monitor night flows with zones, you may find that that causes a problem. So while pressure management, when it works, I think as Neil's indicated, it gives you by far the best paybacks. The other interventions are also important in order to get a balanced strategy. It's very rare that you only need one intervention in an area. It's normally a blend of different, and every area needs a different sort of recipe to get it under control. So maybe that's a bit of a caveat. Here's a nice technical question for you, Neil. I'm sure this will be a quickie. What would the typical operational velocity need to be to operate a pressure reducing valve optimally? What sort of velocity through the valve would be your optimum velocity? And that's from Johan Rudolph.
So it varies from one, let's say the maximum flow rate varies. Sort of the suppliers have slightly different ranges sort of that they give them, and some suppliers prefer up to about 4 meters per second and maybe up to 5 meters per second, but many of them sort of give that sort of as the maximum range, sort of going through the PRV. And on the minimum one, it's not, you know, it's not really the sort of the velocity that goes through is not really relevant. What you need to look at is the opening sort of inside the PRV, is how if there's enough space for the valve to operate, you know, without that hunting effect that we've explained previously.
Okay, thanks, Neil. Here's a nice technical one from Yapi Bota. When you install 2, 3, or 4 PRVs in parallel, how do you decide what size to use? Something that's more readily available off the shelf, such as a 250, or do you base it on what can be handled by the operators, weight-wise? Like, are they great, big, heavy duty farmer type operators, or little thin, skinny guys that can only handle a small one?
No, it's a good question, and I think we've touched on it also previously, in that if you have a very large pipeline and you install a PRV on it, technically you can install a very large PRV. I mean, you get, you know, I showed a photo of a 600 millimeter PRV. I think, you know, you can go larger than that, sort of if required. But number one, it's none of the suppliers in South Africa have stock available for any PRVs larger than 300 millimeter diameter. So if you order anything above a 300 millimeter PRV, normally you would have to wait quite long, you know, for that. If it's a company that imports the valves, you would have to wait for it to be imported. I know some companies cast in South Africa. I don't know if they are casting that very large diameters. So certainly the availability of the valve is definitely one of the considerations that we look at. Number one, if you're going to construct the installation, how quickly can the contractor get that valve? And in the long term, if maintenance, is done on that installation, how readily available are spares for that specific size. So, and the smaller ones, the smaller diameters, well, 300 and below, should be sort of readily available for most of the suppliers. But as you've mentioned, the weight of the valve, certainly it also comes, it is a factor. But I mean, if you install a 300 millimeter valve and you've got some lifting gear, then up to 300 millimeter, it shouldn't really be a problem if you've got some lifting gear that can assist with that.
Okay, I think you showed some pictures of the 3 big installations that you've been personally involved with. In those 3 installations, if I'm not mistaken, they're all 300 diameter valves, are they not?
It varies a bit, Ronnie. I think Kalicha was actually just before me, but I think that was 350 millimeter diameter, but it's a very odd size. And I don't think we've used 350 millimeter PRVs after that. Cebu King was 300 millimeter. Mitchell's Plain was 300 millimeter. And the new Kalicha one is I think it's both 250 on the one side of the installation. There are 2 zones in the new Kalicha installation. So there's 250 millimeter on the one side, and I think a different size on the other side. So it's between 250 and 300. All
right. So it's like it's your large size, but sort of stock items that most metros would hold on their. They'll have spares for them and they'll have them on the shelf generally. Mm-hmm. Okay, thanks for that one. Have there been any, this is from Johan Rudolph, have there been any instances where you had to opt for low-tech solutions such as brake pressure tanks, etc., instead of more mechanically complex and maintenance-intensive PRVs? So have you ever gone for the real low-tech solution, a tank just to break the pressure rather than use a PRV?
I think there are certain use cases for brake pressure tanks, and I know, in some municipalities it's used, effectively, to break the pressure. So I think it's probably if it works in a certain municipality and that's a solution that they use, then I would certainly say that's go for that solution. In other municipalities where they use pressure reducing valves to reduce the pressure, then that's in a solution that they go for. I would say a pressure reducing valve gives you more optionality. I mean, you can set the pressure reducing valve higher or lower, and you can install controllers on it if you want to sort of lower the nighttime pressure. So I would say there are cases where you can use a brake pressure tank, but I would say a PRV probably gives you more optionality. And also if you are inside your water network, I mean, to use a brake pressure tank inside the water network, that may also be a challenge, because I mean, it's going to be difficult to fit that in on the street corner where there's very little space. But you may be able to fit in a narrow PRV chamber on that corner. But so I'd say both have got use cases, but it's it's sort of horses for courses. It's where you want to use it, and if that is the standard way that it's being done in that municipality.
Okay, thanks, Neil. A couple of ones that you can probably cover quickly. What is your view on the current innovation of plastic pilots for PRVs? What do you think of plastic pilots, especially in areas where theft is a big problem? Mm-hmm. And a second question, while you're getting your head around that one, what is your experience? Would you rather use full bore or reduced bore pressure reducing valves? You didn't actually touch on that in your presentation. You might have to just explain to everyone what the difference is between a full bore and a reduced bore and why you would use one and not the other.
Right.
So plastic pilot and reduced bore PRVs.
Right. So on the plastic pilot valves, I mean, I know there are some municipalities that use that extensively, exactly for that reason that was mentioned, sort of the theft problem. Sort of we personally, I mean, I've sort of heard, let's say, mixed. I've received mixed feedback on the plastic pilots. I think, you know, I've certainly heard from people that there are cases where the plastic pilots work well, and it certainly they certainly lower theft and vandalism at those PRV chambers. I've also heard from operational staff that those plastic pilots have given some problems, you know, after a certain period. I haven't been able to get the exact details of, you know, whether the pilot body itself cracked or sort of what happened sort of in those cases. So yeah, so I'm sort of, you know, talking on what I've heard from other people, and some have said that it's working well for them, but I've also heard from others that the plastic pilots have been giving, you know, them problems sort of over time. So my suggestion would be, as it is for most options, is if theft is a problem in your municipality, then certainly try the plastic pilots, I think, you know, for some of your PRV installations, and monitor it and see how stable the pressure is that you get from those plastic pilot valves, and how, you know, how long they last sort of compared to other pilot valves. And if it works well in a municipality, then certainly that is an option that can be considered. But I would like to just go back to my slide of the snake and the lockable chamber, that I would, you know, before even considering what pilot valves are to use, if it is possible to keep the people out of the PRV chamber, that would be my first option. Because, I mean, you may also want to have a data logger installed in that same chamber. So if you've got a plastic pilot valve, but a data logger next to the PRV, and someone is still able to get into the chamber, they may steal the data logger. So then it doesn't really help you a lot, you know, by installing the plastic pilot valve. So I would say first prize is try to get to chambers so that, you know, people cannot, sort of vandals cannot get into the chamber. That would be first.
I think I'd agree with that. Also, the fact, if you've even got brass couplings or any brass fittings that you use on the pilot on top of the valve, anything that's brass that can be taken off will be taken off, whether there's a plastic pilot or not. So I think I echo, ideally, first prize, keep them out of the chamber at all costs, whether you use a concrete lid or snakes, or I think Andre in Drakenstein uses mustard gas in his chambers, and that seems to work quite well.
Yeah,
it's getting a bit drastic, but it works.
Zubair from Drakenstein is going to talk tomorrow, so he can inform us how it works in Drakenstein. I know some of our technicians have did some logging at some of their PRV chambers. And if something goes wrong, if someone gets into the chamber and you are not very quick to type in the keypad that unlock code, that
you need a gas mask, right?
Goes off. You're not. No one is able to get close to that chamber. So it certainly seems to work.
All right, okay. The second part of the question was the reduced bore. Yeah.
The reduced bore versus full bore. It would basically, so what it means is a full bore means that the seat inside your PRV is the same diameter as the inlet and the outlet of your PRV. So if you have 100 millimeter diameter PRV, then the seat would also be 100 millimeter diameter. That would be a full bore PRV. If you've got a reduced bore PRV, it would normally be, the seat would normally be one size below the inlet and outlet of the PRV. So a reduced bore 100 millimeter diameter PRV would normally have an 80 millimeter seat, thereabouts, more or less an 80 millimeter seat diameter. the reason why reduced bore PRVs are used, I mean, there are a few reasons, but the one is that the suppliers know that many PRVs are oversized. So they know if someone orders sort of 100 millimeter PRV, there's a good chance that that PRV is going to be oversized. So if the seat inside the PRV is an 80 millimeter, there's many a times a good chance that that 80 millimeter is actually going to be better suited to the flow that's going to go through that valve. And that slightly smaller seat size means that as the water now flows through the PRV, the valve, sorry, this is getting a bit technical for the non-PRV people, but the valve, the sealing disc is moving then slightly higher up from the seat, so it gives the valve a bit more room to move up and down, that you don't get that hunting effect. So that's what that smaller seat size does. The other benefit that you also can get from a reduced bore valve is, in some cases, you can get a slightly better cavitation protection, because of that slightly smaller reduced bore, there's normally a bit of an opening, a gap inside the valve between the seat and where the valve body starts. So if you do get cavitation inside the reduced bore valve, normally the valve can handle a bit slightly better than a full bore valve, and therefore the PRV suppliers normally allow you that the pressure reduction ratio over the valve, they normally allow a slightly higher ratio if you have a reduced bore valve versus if you have a full bore valve.
Okay, thank you, Neil. I'm going to, although I'm actually running into the question time at the end, I'm not going, I'll make sure our next two speakers get their full hour, so they mustn't worry there. But I'd like to just, a couple of questions, this is that are quite interesting. Just before I go on to these last two questions, when you were talking about the reduced bore and such like, I think one of the most common mistakes made when putting in pressure reducing valves is a lot of people, if it's a 300 millimeter diameter pipe, many people don't worry about sizing the PRV. It just looks good if you put a 300 diameter PRV on a 300 diameter pipe. And the reality of the situation is it should normally be at least one size or maybe even two sizes smaller to get that velocity through the PRV that it likes to operate at. Neil, maybe you just comment on that?
Yes, correct, Ronnie. So there's not really a thumbsuck rule that will work in all cases, but certainly there would be very few scenarios where the PRV would need to be the same size as the pipe. So normally that would normally be a good starting point, that the PRV and the water meter, the bulk water meter, in most cases will be smaller than the pipe diameter.
Okay.
But if it is possible to get the actual data, whether you do some pressure and flow logging or whether you use a hydraulic model to get the flows, if you've got that data, it's making the sizing much easier. And on sizing, what my recommendation normally is to gather all the flow and pressure data and everything that you can, and then send that data to one or more of the suppliers that you think you would sort of like to use. And those suppliers are normally more than happy to punch those numbers in the sizing programs, and they would suggest to you what valve will work best and where you need to watch out for certain pitfalls. I mean, the suppliers are quite helpful in that regard.
Okay. The next question is actually one that is one of my favorites, so it's a pet topic of mine. It comes from Koki, and the question is, what measures, technology-based in brackets, should one take to ensure that the integrity of the zone is not compromised by maintenance and operations personnel? And I think this question basically hits the nail on the head when it comes to pressure management. Neil, I think you've done how many thousand zones that you've had to recommission. What is your answer to that one? How do we keep the pressure zones discrete?
Yeah. No, Corky, you touch on a very important point there. I mean, I didn't actually discuss it in my presentation. It was one of the questions that I slipped in there to see if people can pick up on that cross boundary point. It's that problem that you're talking about in that question is, we've seen that in every single municipality. We've looked at PRV zones. And, you know, in some of the cases where we did large projects where we serviced, you know, many PRVs, it almost felt to me like half of the zones had a problem at the PRV and the other half of the zones had a problem with non-discreteness of those zones. So it's a significant problem. So there are some solutions in terms of locks that you can install on those. Let's say if you use boundary valves, so there are suppliers that's got locks available that you fit over the boundary valve, and then the idea is that only certain people in the operations team will have, you know, keys to open those locks, and those locks they work with varying degrees of success. You know, some work a bit better and some not so good. There are also municipalities like Tshwane and eThekwini, where they make a decision that if there is a cross-boundary pipe, they physically cap the pipe at that position, and then they install an above-ground hydrant, you know, on the left and on the right of that capped pipe. So you've got two hydrants sticking up like that. So, which is, I quite like that solution in that for new people coming into the network, it's very easy to see where the zone boundary is, because you just look for those above ground hydrants. And then also, if there really is a crisis and you need to convey water from the one zone to the next, because those hydrants are placed so close to each other, you are able to install a temporary connection from the one hydrant to the next to at least get some water over to the next zone. But because it's an above ground, it's very easy to see there is a cross-boundary connection. So it's easy to come later and make sure that cross-boundary connection is removed. And then lastly, what I'll mention is, where possible, we recommend that you install permanent flow and pressure logging in PRV zones. So again, I realize it's not feasible for every small PRV zone to install that, but for any medium and large PRV zone, we would recommend install flow and pressure loggers, and then you set up alarms so that the moment that the flow or pressure should change significantly, that you receive an alarm, you will not know, immediately that it was a valve that was opened or closed, but at least you will be aware that there is a problem, and then someone can go out and investigate to locate the problem.
Okay, thank you, Neil. I think it's important to say that the zones, keeping the pressure zones discrete, is without a doubt the biggest and most serious problem issue we face when implementing pressure management. 6 months down the road after you've commissioned a zone, the zone is no longer a zone. It's been totally messed up. So if you are implementing pressure management, part of the deal is that you implement a system of ensuring that the zones remain discrete forever. It's not something you do now and forget about it. It's something you have to do every single month or every 6 months to make sure the zones are discrete. Otherwise, everything you've done, all the money you've spent on the PRV is wasted. So I think that's a really critical question. One last question, Neil, before we go on. I'm not going to be able to, you've got a whole bunch of questions here. Everyone's asking questions, which is good. We want them all. We'll try and answer them at the end. But just one very quick one from Peter. We worked with you on a project in 2013 and 14, which I can only assume is the Johannesburg Pressure Management Project. And he would like your honest opinion. He wants your honest opinion. He doesn't want a political answer here on how much did the hydraulic model support you and your team? There's a question for you. Did you need the hydraulic model, or could you have done it without the hydraulic model? And we want an honest opinion. We'll see which way your eyes are looking. If you're up to the left or the right, whatever.
Okay, I would say, I mean, over the years, we have done pressure management projects without an hydraulic model. So it is possible to do pressure management without hydraulic modeling. But where possible, I would recommend that you do hydraulic modeling. It's just going to give you, it's going to give you more information. It gives you more optionality, because you may be focused on doing pressure management in one specific zone, but if you run it on a hydraulic model, you may see, but there's a problem in the adjacent area also. So maybe you can alter sort of the zone boundary and achieve even greater water savings. So my short answer is, it is possible to implement pressure management without an hydraulic model if you carefully get all the data. But where possible, if you can do the hydraulic modeling, it will just give you more optionality and make your life a bit easier.
Okay, I'm sure that's the answer Peter would have liked to hear. Thank you for that, Neil. Okay, I'm sorry I'm not going to go through the rest of the questions just now. We'll try and come back to them after the next two presenters. We're going to, Neil, I think, thank you for a wonderful presentation and for answering as many questions as you did. I'll expect you back in an hour to answer a few more that are still unanswered. But in the meantime, we would like to throw, you can, I'll introduce Unati Nolodwe. Is that, I hope I've pronounced that. Unati Nolodwe from the city of Cape Town. I hope I've got your name right, Unati. I apologize if my Scottish pronunciation is not all it should be. You are from the city of Cape Town, the water demand management section. You've got a national diploma in civil engineering and a BTEC in civil engineering. You're the senior technician responsible for managing leak detection and alternative water sources for the city of Cape Town. And we would like you to, that's it, well done. Yes, caught it before I even mentioned it. Brilliant, you've got the presentation up and running. The floor is yours. I'm going to give you half an hour, and we'll see how you get on. If you finish early, we'll just ask you lots more questions. And if you finish late, we'll deal with that when it happens. All right, thank you. The floor is yours.
Thank you, Ronnie, for the introduction. Good afternoon to everyone. Yes, you've pronounced it right. Yes, I am Unati Nolodwe from the city of Cape Town. I will be doing leak detection at the city of Cape Town. So this is my presentation outline. I'm not gonna go through it. Yeah, starting with the introduction. According to water demand management and strategy, the best ways to minimize water losses in the reticulation network, starting with the easiest to implement, are pressure management, leak detection, speed and quality of repairs, pipe replacement. It is therefore means attention is needed in leak detection as more pressure management zones become available. Currently, we are at 60% coverage of the zone at the city of Cape Town. In our water balance, leak detection aims to reduce the physical losses that we know that will benefit in reducing the non-revenue water. Why are we doing leak detection? we detect the existing visible leaks. There are those leaks that are not reported, that go unnoticed for a lengthy period of time. We detect existing non-visible leaks, use different leak detection equipment to detect noise emitting from reticulation network, such as valves, fire hydrants, and service connections. We give support also to reticulation depots to pinpoint and locate the location of the existing leaks. As we know that water finds the way of escape, that is necessarily not where it is originating from. So we detect the origin of those leaks. Also improve repair response time by reporting all the leaks, by creating a C3 notification to the relevant depot, and so that the depot can attend to them and repair those leaks. So the target response time is 2 days. The equipment that we use as the City of Cape Town, it's mechanical listening stick. It is used in all contact points, such as meters, valves, fire hydrants, to detect the noise emitting from the possible leaks. We also have the electrical listening stick, but mechanical seems to be working best for us. I guess our hearing ability is too sharp. We also use noise lockers. Noise lockers are deployed on every pipe fitting, such as valves, fire hydrants, can be valve to valve or valve to fire hydrant, detecting the noise emitting from the possible leaks. We program them over a predetermined period of time to record any leakage noise. As Stuart mentioned, the best time it is 2 a.m. to 4 a.m. We then download the data that is recorded over that period of time so that we can start to analyze where the possibility of a leak is. The data that we get, we interpret the ESA value. If the ESA value is low, it's more likely that there is no leak. And then if we see the spectrum red, then there is a possibility of a leak. And then if it's yellow, it's very likely that there is a leak in that position. Then we use leak noise correlator now to locate the leak. Fire hydrants, valves, meters are used as a point of entry to the pipeline. You must know your pipe details, such as the pipe material, pipe diameter, and then you measure the distance between your two sensors. The picture that is coming up now, after you have done your correlation, where your correlation curve is, you measure. In this screen, it's showing that it is closer to sensor B. So we'll measure from sensor B to where the leak is, your 10.2. You then use your ground microphone now to pinpoint or confirm the coloration results that you have got now to pinpoint the leak. So ground microphone, it is used, it does not need any contact point. You can use it on the surface of the ground. You move it along the ground surface, the pipeline located underground. So the principle of this device, the closer you are to the leak, the greater will be the leak noise. We also use the temporal data loggers on the DMAs that doesn't have permanent controllers. It is used to measure the flow and the pressure in order to analyze your minimum net flow. Then another equipment, it's GPR, the ground penetrating radar. we use it to locate the services that are underground, mostly to locate the pipe direction and the depth. If we are working in an area, we are not sure whether the pipe stops here or it continues or which direction is it moving. We use this equipment. It is very helpful so that we know as we use our ground microphone, we are on the where the pipeline is running. So the methods that we use for leak detection, it's 4 methods: visual leak detection, whereby the team goes and drives or walk on the street to inspect the reticulation network for obvious ground leaks on the reticulation network or on the service connections. So we have a 3-kilometer target per team per day. We then localize leak noise survey by using listening stick and noise loggers. Then we locate by identifying the leak location by using leak noise correlator. Then we pinpoint and confirm with the ground microphone. Step test is part of the process. As we start with a bigger area, then we isolate it into smaller sections while monitoring the flow. So the best time is to do it at night when the demand is less, because we'll be shutting off some valves. Then while you are sectorizing your areas, you keep on monitoring your flow. Then where there is a disproportionate drop in flow, that's where the suspected leak is. Now that's where your focus will be. So you start from bigger area, you shut it down into smaller section until you get where the suspected leak is. Then where you will continue now using your methods of leak detection to identify where the leak is. The approach to leak detection there are different approaches that we use. Then for the areas that are non-discrete, we use this approach of a scorecard, whereby we need to know the type of material, age of infrastructure, average pressure, pipe burst records, the soil type, the period of supply, was the leak detection ever done in the area, and also the type of land use. Is it residential area or is it industrial areas? Because also that is very important to know, because you might have your minimum net flow very high, only to find out some areas they've got industrial. There are some businesses that takes place during the night period. So you rate your scorecard, then the areas that have high score, you will target to start doing your leak detection in those areas. Then for the ones that are discrete, we use the zone analysis, because our zones are monitored by controllers such as I2O, ZNet, My City Logger, and then we analyze the minimum net flow over the average flow. Then for all the zones that they give 30% of the average flow, we target those zones to start with. We also use the sand flow model, where for each zone, you must know your minimum net flow, your average pressure, the length of main, number of connections, number of properties, residential population. And then it will give you an expected leakage And then if it is above the threshold that you expect, you can target those zones. We also do some calculate the unavoidable annual rail losses. So for all the zones that are above 30%, we target those areas first to start with, because at the end of the day, we want to see results and reduce that minimum night flow. This is an example of a zone with a high minimum net flow. Prv, it had 8.6 cubic meters per hour, and then the average flow is 16.9, and then the percent that we got there is 52.4. So it's an indication that leak detection must be prioritized in that zone. So for the past 3 years, we have managed to cover the whole of the City of Cape Town network using non-visual. It's only the last financial year whereby we started to use the equipment looking for the non-visible leaks. So per year, we cover the half of the reticulation network. So for all the leaks that were detected by the team, C3 notification we created, sending to the depots to attend to them and fix them. So all the leaks were fixed, but not all of them. The turnaround was 48 hours. We still aim to repair those leaks within the 48 hours. For the past 3 years, most leaks were occurring from the meters, then service connections, valves, fire hydrants, not much on the main. Then the list was the stopcock. This is an indication why the response time is very important, because the volume you get, the volume for each leak, you multiply it with the response time. So if the leak took a day to be repaired, that means there is less water lost. But if the response repair time period takes longer, it means that you will have much water that we are losing. Also, the location curation, also it's also important to note. If it takes you 5 days, if it takes you, okay, for awareness duration, it's most likely that you want to know, you will start on the day that you were aware that there is a leak, and then your location duration, if it takes you 3 days, that means now it's 4 days. Then the repair period, if it takes 5 days, then now you are now having a longer period in attending to the leak. So that is, we must try by all means to reduce so that we can save water as much as we can. So these are just the pictures of the leaks that we have found. The first picture, it's a valve. Already the grass around it, it's an indication that that leak, it's been there for a period of time, because around it, it's not as green as it is closer to the valve. And also we using that listing stick to confirm that it's not just the standstill water that is inside the valve chamber, but it is a continuous leak. Then from fire hydrants, service connections, and also around this meter, you can see this is a pavement, but around it, it's green. There's a green grass. So also that as you are walking, approaching the meter, you already know, you are already suspecting that there is a leak there. So, and also some pictures from the leaks that were underground. and the first leak was on the main and then the service connections. And the last picture, you can tell already that that leak was caused by the roots. That those 3 roots, they are the ones that diverted the direction of the pipe, and it ended up breaking. My last slide. So the future of leak detection at the city. We aim to conduct leak detection on bulk meters, on bulk network also, increase leak detection team in order to do 100% coverage every year. Then to pilot and explore new leak detection technology with the best benefits. Yeah, that's it from me. Thanks for the opportunity. Thank you for listening.
Thank you, Unati. That was very well done. And you put in a really nice presentation there with some lovely slides of what you've been up to. And I think what I'd like to do, if possible, rather than take questions just now, I'll maybe ask 1 or 2 very quick questions. We're going to have a question session after the next speaker, and we can throw them all together. Would that be okay with you if we do it that way?
Yes, that's okay with me, Ronnie.
Good, good. You don't have another meeting you're going to duck off to in the meantime, like Stuart would have done. That's good. I want a couple of things. It was very interesting, the fact that you almost repeated what Stuart showed on all the different things as to what to do. This is, he's going to do this. I mean, you're doing them all. Have you been talking to Stuart, or was that pure coincidence?
I guess the approach is the same. So I'm learning from the best.
All right. Okay.
I was actually happy about Stuart starting, because I didn't have to go into detail now on equipment. At least people have an understanding.
All right, because you showed all the equipment that Stuart was showing, and it's like, I noticed that you had lady people operating all the equipment with good hearing. Is that a deliberate ploy in Cape Town, or is there any job there for kind of a Stuart sort of person that's hard of hearing? Is there still room for him there, do you think?
I cannot answer that one.
All right, okay, no, that's good. That's a diplomatic answer. That's wonderful. No, that's all right. No, that was good. No, I was very impressed with what you're doing. The one question I'd like to ask is, you mentioned that you've got 60% of your area under pressure management. What is your target percentage that you're looking to try and achieve over the next 10 years?
Yeah, the next speaker will be talking on pressure management.
All right, so we keep that question for question for the next speaker. Okay, I won't steal our thunder then. Perfect. Okay, I'm going to save the questions for you until after the next speaker has finished, and then we'll throw all the questions together and try and do a big thing like that at the end, if that works for you. Thank you for a very informative and well set out presentation. I would like to introduce our last speaker for the day, and this is Ivy Masela. Ivy Masela, also from the city of Cape Town, also from the Water Demand Management section, also with a National Diploma in Civil Engineering and a BTEC in Civil Engineering. And you're a senior professional officer managing a team responsible for, amongst other things, treated effluent, pressure management, DMAs, leak detection, etc. And I understand that the subject matter for your presentation this afternoon is going to concentrate on the pressure management side mainly, is that correct?
Yes, that's correct, Ronnie. Thank you very much.
Good.
Yes.
Okay, I'm going to hand over to you, and then we'll push the question. I'll go through all. lots of I just need to write all the questions down so that I can ask them to Unati and yourself and Neil at the end of your presentation. Okay, the floor is yours.
Thank you very much. Good afternoon, everyone. Thank you for the opportunity to present on our pressure management work that we've done over the years in Cape Town, and most importantly, present where we are now and the direction that we headed with regards to pressure management, most importantly, and other water demand management interventions. I've been already introduced. My name is Ivy Masela. I'm with Water Demand Management. So the presentation overview will cover the following. I'll briefly just share where we get our water from and share basic information about our distribution system, the legal framework and strategies from which we operate, and why we implement pressure management in the city of Cape Town, our approach to pressure management, our zone monitoring approach, and our different types of controls currently in place, Prv controls in place, and information on savings. I've got some information on non-revenue water and how we are intending to address non-revenue water in the city as things are, and our challenges as well. I'll share that. And also our future interventions, and I will conclude. So this presentation is going to obviously tap off from what Neil has introduced to a great detail and very well in terms of pressure management. I'll focus more into what in the city of Cape Town we are doing with regards to pressure management. Basically, this is how water is supplied to the city of Cape Town. We basically receive our water from 6 main water dams, spatially positioned across the Western Cape. Our allocation of water is 347 million cubic meters per annum. Our current water sources are mainly groundwater and surface water. Surface water constitutes to 96% of the water, and groundwater, as at when our water strategy was compiled, it was 4%. We are now going through a process as a city where we're implementing various projects focusing on exploring diverse water sources. And we're looking at desalination, which would eventually by 2040 contribute to 11%. Groundwater will increase from the 4% to 7%, and reuse, which is reclamation, that will be at 7%. Then this will hopefully drive down our dependence on surface water to about 75% in 2040. Just some basic information on water supply and our distribution system. We serve a population of 4.7 million people. We have over 600,000 connections. This is the exact number. And some information around the mains, the pipelines, the networks itself. Excluding bulk water, our current network, the reticulation network, is 10,977 kilometers, of which 7,698 is under some sort of pressure control, which means that we do have pressure reducing valves installed, and not all of them strategically installed, but this length of main is under some pressure reduction management. We've got 92 kilometers that is district metered areas and also being monitored as district metered areas. We've got 63 kilometers that falls within a category of booster zones. These are zones that we cannot pressure manage because the pressure in these areas supply areas downstream, and that pressure is required. So these areas tend to operate at fairly high pressures, and we don't have intention to pressure manage in the future. In total, 70% of our reticulation network has some sort of pressure reduction valves or pressure reduction control taking place. It's not optimized, it's not the whole 70% that's optimized. However, there are pressure reducing valves controlling about 70% of the pipelines. In terms of zones, we've got an ultimate number as things are now. We've got an ultimate number of 376 water zones in the city. Of these, we have 236, just over 60% of our zones are established and discreteness has been confirmed for these zones. So it's just over 60% of the zones. The number of the ultimate number of zones tends to change as and when we create new zones. That number moves with that target. Our legal framework and strategy for pressure management is the following document. So basically, the National Water Act and the Water Services Act provides makes a provision for the need for pressure management, as it's expected that as water services authorities, we are expected to implement water conservation and water demand management interventions. And therefore, our integrated development plan as well, there's an expectation that we are to put measures in place to prolong water infrastructure. And also the water strategy goes into depth in terms of commitments with regards to water security in Cape Town. And commitment 2 speaks to wise use, and pressure management is an integral part of wise use, and also reducing non-revenue water and reducing losses. We also have the water demand management strategy, which was the latest, was updated in 2017. That is very specific to our intervention in terms of measuring all water going in and being supplied to all our customers. Most importantly, also monitoring that the pressures are of an acceptable margin, and that we are efficiently supplying water to the customers. The Water and Sanitation Department's vision is to be the beacon in Africa through progressive realization that Cape Town is a water sensitive city. This is the vision of our executive director, Mr. Michael Webster. And this is the vision that we live by on a daily basis, to put together programs and projects that align with this vision. The reason why we in the city of Cape Town implement pressure management is firstly around the distribution network itself, the failure of the distribution network. And this failure happens for various reasons. Amongst these reasons is our infrastructure is aging, and there's a lot of failure in the joints of our pipelines. And also the current network, or our network distribution network pressures are relatively high, which are beyond the 90-meter recommendations by most guidelines. So we strive to reduce those pressures to acceptable pressure operations. And also our pipeline, our distribution system fails because of also poor workmanship. And this could be during routine maintenance where we are responding to bursts, or it could be when we have outsourced infrastructure to be constructed. That could be the reason for the poor workmanship as well. And it's also because our infrastructure fails due to the daily operations of the infrastructure. As when we report to bursts, how we charge our lines up after that, the air pockets in our mains, and also pipe surges also affect our infrastructure. So that is the reason why we implement pressure management. The benefits of us implementing pressure management, we immediately see the benefits when we reduce pipe bursts, which means indirectly we also reduce, or directly we actually reduce operational costs for the repairs. And most importantly, we reduce leakage. And then we also have water savings that we benefit from when we reduce pressure in our systems. And when we reduce pressure, we also extend the infrastructure lifespan. We also postpone infrastructure upgrades. So pressure management in the city now goes hand in hand with pipe replacement programs. To a certain degree, it contributed largely to the postponing of major upgrades within the system itself. Our approach to pressure management in the city of Cape Town is that of a process-based approach. We are ISO 9001 certified, so we try our best, and we are motivated to maintain the certification. And in that motivation, we ensure that we have processes in place. We've got procedures in place for activities. We've got flow processes. We've got works instructions in place. We follow templates. So we've got a standardized way in which we approach pressure management as the city of Cape Town. And also we've got a 10-year plan on how we intend to cover the remainder of the system, and also to improve zone management within city of Cape Town. So we do have a 10-year plan. And we also have an approach for how we prioritize the areas in which we implement pressure management. And this prioritization, we do an analysis of our pipe burst stats. We look at pipe material. We look at the average theoretical pressure or system pressures to prioritize the areas in which we implement pressure management. From year to year, we review the areas and over a period of time. And our zone management work entails designs. In the city of Cape Town, over the years, we have started using internal teams to design easy or straightforward type of zones. So zone management for non-complex areas is done internally. We outsource complex zones or big zones. We outsource it to the companies that design zones for a living through formal tender processes. We also do construction supervision after designs have been implemented. So that is part of the work that we do internally, which is the supervising the installation of the zone infrastructure as listed here. And part of the zone design also entails analyzing and checking the viability of controllers. So we also look at that in the city of Cape Town. We look at the viability or the need for a controller to be installed. Our objective overall is to install at least loggers on almost all of our zones across the city. We are not there yet. We are although working towards that plan. After completion of construction work for our zones, we actually produce closeout reports. And even when we outsource the construction supervision, we expect the consultants to produce closeout reports. And we also compile as-built drawings. We have over time now improved the quality of the as-built drawings, which I'll share later. We've got a zone as-built drawing. based on lessons learned. And also the information, the zone information that we capture on the field, we share with our GIS team, which is responsible for capturing the assets and also maintaining our GIS asset information. From time to time, we do receive operations and maintenance manuals from the contractors. This usually depends on the complexity of the zones. And after we've also constructed and we've installed the PRVs and the meters and all other infrastructure that accompany the zones, we hand over the infrastructure information to our engineering and asset management reliability section for capturing on SAP. We use SAP as our main asset register platform and asset management. That information is captured, and also dates are captured for mostly proactive maintenance, where there's a proactive maintenance plan that's put in place for those specific PRVs. And that is something that over the years we are improving. And yes. As I said about our approach to pressure management, pipe burst plays a critical role to our approach. This is the data that is based on bursts that have occurred in 2020, that financial year 2020. You will see that a lot of our bursts have occurred around this is the southern suburbs, in the Newlands area, Rondebosch areas. That's where we had to deal with a lot of bursts as the city. And also out in the northern suburbs, in the Devonville area, there was also a significant amount of bursts. And this is Somerset West. There was also a significant amount of bursts. So that's the key data that we look at when we look at the approach. Theoretical system pressures, we obtained that from our colleagues. It's also still within the city of Cape Town, who run the hydraulic model for the city. So they provide us with the theoretical pressures that are within the area, so that we can overlap to be able to prioritize appropriately. The same thing that happens we follow the same approach as well when we're looking at the pipe material. Over 50% of our network, it still has AC pipes and or fiber cement pipes material. So we know that those are sensitive. So we overlap the pipe burst and the pipe material as part of the matrix for our approach to prioritizing pressure management. We try to cover 3 to 5% of the network annually, and this coverage is not only for pressure management per se, it's just generally zone management. So this includes also district metered areas. Over the years, we have improved our alignment of pipe replacement and pressure management interventions. The critical part of our zone management, of our pressure management zone design, we have found that it is to confirm and verify the discreteness of the zone. Even after we have designed a zone, and it's in other instances, even when we have outsourced the design of a zone, we still go back in with our technical guys and confirm the discreteness of the zone. So this is a typical example of such work that we've done. This is a process, this is a near zero pressure test stage that is part of the processes that we follow in designing pressure zones or zones in general. So in this layout, you'll see that this is the proposed extent of the zone. We've identified, or the designers, actually this zone was designed by WRP, if I'm correct. They identified they proposed potential boundary valves that should be isolated, and they identified where the supplies should be. But prior to us going into construction or to us allocating the work to the contractor, we go back in and check the discreteness of the zone using the information on the design report. And this is the logging data that will be analyzed from that stage, where we log both inside and outside the zone, and we identify the inflows, we isolate as per the proposed design, and we check the zone discreteness. And when we get a profile like this, we are very happy because it means that the zone is discrete. This is a typical photographs of what our infrastructure looks like. This is the components that we find in most of our established zone chambers. We've got a strainer, emitter, the pressure reducing valve itself, and an air valve. This is a critical point chamber. Due to theft and vandalism, we've had to evolve in terms of material selection and also how we construct our critical point chambers. So this is a typical one that you will find in a not so safe area to connect a logger, because we monitor our critical points. This is a typical critical point that you'd find in a relatively safe area. This is a photograph of a completed installation and what you would be able to see, where we've got valve markers, and it's very clear to see the upstream side of the supply. Yes, and also this is a photograph of a data logger that was installed, that has been installed at the critical point to monitor the pressure at the critical point. Over the years, we've had to revise and refine zone as-built drawings. So in the last 3 years, we have really gained confidence in this to an extent where we are working towards a standard approach of as-built. This is a typical example, and this is all in the efforts to maintain the integrity of our zones so that they do not get breached. And in the event that the zones are breached, we know exactly where to go. So this is the typical drawing that will show such information. You see that on the left-hand side, it shows the boundary valves, the exact coordinates where they are. It shows under which region it falls under. It shows the zone detail information. We also include here the length of main, number of properties. So this is the basic zone information that now, over a period of time, we've decided to incorporate or consolidate into one drawing. Our monitoring of zones, we monitor our zones remotely for mainly the established zones, and this was mostly fast-tracked through the drought, where we had to appoint a service provider to supply us, or service providers to supply us with loggers and controllers for our zones. So we monitor those and ensure their discreteness. And our monitoring system also has alarm settings in them that notify operations when there are zone change, when there are changes in the operations of the zones. We do produce monthly reports that also inform the operations on how the zones are performing. Internally, we produce internal reports just to confirm if all information on the zone, especially the information that's accessible to all City of Cape Town employees in terms of the upstream pressure, downstream pressure, and also the flow profile, if all of that information is still available on the platform. So we continuously try to monitor that, and we've got a tender in place, and we try to maintain that to maintain the infrastructure and take care of the licensing as well. So this is a typical zone. This is in District 4, in Region 2. It's clean phase zone. You will see here that this is the concept that Neil was explaining in terms of the fixed outlet approach, and this was the leak detection that Unati was speaking to, the leak detection information, what would activate leak detection in terms of the average flow versus the minimum night flow. In our pressure management control, as Neil has explained, the concept of the different ways in which zones can be controlled, or pressures can be controlled within the system. The one that the City of Cape Town has adopted, and over time for big zones has gained a lot of savings and benefited a lot from, is the time control. This is a typical example of such, where we've got the Brooklyn zone, where this is the upstream pressure. It's around 100 meter head. And then this is the time control, where at night we push the pressure down to about 40 meters. And then in the morning during peak, when everyone is requiring the water to do their morning activities throughout the day, we then open up the system, or the system automatically at that time opens up, and then in the afternoon it closes down again. The controller it tells the PRV to start closing down to the reduced pressure, and then we further reduce the pressure, and this has had a positive impact in terms of reducing pipe bursts in this zone. And we also monitor the critical point. The green line is the critical point. So we also monitor that, just to make sure that we still provide the minimum requirement that we've put in place, that will supply a minimum of 24 meters of pressure at the critical point. So we always monitor that to just make sure that we are within that. And if we are not, we then go out, we send teams out from time to time to go and do valve verification in our zones. So this is the zone coverage, just to get an indication of the zone coverage. We have split our regions into 4 regions of the network. This is more or less the number of zones, pressure management zones, that are within those within the regions. These are the savings that we've realized through pressure management. The biggest savings that we realized was through the drought response. The initial plan was the target was around 52 megaliters a day, but with everybody involved and everybody working together, through just pressure management alone, we're able to realize 70 megaliters a day of saving. Obviously, as the restrictions were relaxed, we did see that reducing over the period of time. When we did bring new pressure zones into the system, the savings increased, and over time, when we had to increase pressure to about 25 meters at the critical point, then the savings reduced. We are currently around 20 megaliters a day in savings through pressure management. This is just a graphical view of our non-revenue. So this is the system input volumes over the years. I just did an extract from 2010 to date. This is the system input volume over the years again. This is the volume of non-revenue that we've officially recorded. You will note that from 2015 to date, from 2015 to 2019 or 2018, the system input volume was reducing. However, that was not a reflection, so that the non-revenue volume did not correspond with the system input volume as it was reducing. And at the moment, we have explored various reasons as to why this may be so. We did note that now in this last few years, we've actually had an increase in percentage of non-revenue rather than reduction. And we do suspect that is a combination of different issues around accuracy of meter reading, accuracy of data. We've also picked up through our meter audit program that our meters are oversized, especially in industrial areas, and that we suspect that could have contributed to that. And also definitely the increase in pressure after 2018, the increase in pressure now working towards the critical point pressure of 25 meters, that also may have played a role in the increase in the percentage of non-revenue. There are key focus areas that have now been established by the City of Cape Town to try and address our non-revenue percentage. We, as I said, we're currently sitting at about 34%. So the Director of Distribution established a steering committee for non-revenue to find a way to integrate or to improve the integration of approach to non-revenue. So in this steering committee, there is reporting that happens in line with meter audits and meter replacement programs, and this is from bulk. So the bulk meter audit and meter replacement program reports to this platform and provides feedback as and when the meetings take place. Pipe replacement program also reports to this platform. Leak detection reports to the platform. Pressure management reports to the platform. We've also started looking at the zonal water balance, the bottom up approach to the water balance, where we produce water balances for the individual zones that we've created, the discrete zones. This is still a work in progress. But this also reports to this platform, and also the asset management part of it also contributes to the platform, and also education and awareness programs that report or that is also part of the focus areas in terms of reducing non-revenue water. Our current challenges in the city with regards to pressure management, but most of all as well non-revenue, is the reporting inaccuracies, mostly which is from the meter information. It's also the fact that our zones, they get breached more often than not, which is why we have focused on improving our as-built drawings. And the fact that our controllers and loggers are the licenses are owned by third parties, so there is a lot of red tape around that within the procurement process with that. So that's the challenge that we're currently going through. The turnaround time for repairs of PRVs when they fail, because our PRVs tend to fail often. So when they do fail, the turnaround time for those repairs and the processes that are followed within those repairs, we still have challenges with that. We are working on that. A main one is the procurement expectations, because we cannot specify brand names. So we tend to be limited to specifying what the operations should be. And then we've got different brands or different manufacturers of the pressure reducing valves on the field, but then our employees are not all trained, or we don't know how to service all types of PRVs. So that has been a challenge for us. Availability of spares has been a challenge for us. Definitely aging infrastructure has been a main challenge for us. Loss of skills and institutional knowledge, that has been a challenge that through the ISO 9001 and the system approach, we have been trying to address by having standard operating procedures, having templates, documenting everything that is being done within the institution. Quality of workmanship has been a challenge. Maintenance of meters within the city, that has been a challenge as well, which is being looked at. Definitely the issues around oversizing that has been brought up, and we are addressing those through the different committees. The other challenge has been, now that we are working towards pinpointing exactly why our non-revenue water is increasing. So that working towards pinpointing that, we've highlighted it as a challenge, and all the teams that do interventions that are linked to non-revenue are coming together to work towards contributing to that. So the future of pressure management, basically this is the zone coverage. So this is not the network coverage, it's a zone coverage. We are hoping to cover the whole city. Hopefully by 2028, we would have had a full coverage of our zones. This means that by 2028, we're hoping that we're going to have proper zones. We'll know exactly where the boundary valves are. We will have as-builts similar to what I've shown the example for all our zones across the city. And for every year, we have indicated the potential savings that would be realized through that zone management intervention for that year. This is the projected capital budget requirements for both refurbishment and new infrastructure. We've focused more as well on the operation part of things, to keep our licenses up to date for the loggers and controllers that are that are owned by third parties. Future interventions are metering and monitoring of reservoir outlets. That's one of our key future interventions, and also we would like into the future to have reservoir water balances as well. We also want to increase visibility on the 70% of the network that's currently under pressure management, because it's not the complete 70% that we have the ability to monitor and actually report performance on. So that is also part of into the future projects. We intend to install meters at our current Prv zones. We do have a lot of those old zones that do not have meters installed. So as part of the refurbishment works, these have been identified in our plans for future projects. And also to focus more on district metered areas being established within our industrial areas to give a close monitoring at the leakage levels, especially within the industrial areas. This is mainly because we did pick up that with the oversizing, it does affect our ability to monitor the impact of leakage levels or even consumption levels within there. And definitely to pilot new technology as far as leak detection is concerned, because that's one of our newer programs as water demand management. We've already invested quite a lot in equipment in the past 3 years. We've purchased equipment of over 3 million, and we've got an established team. So we would like to explore that further. The conclusion is a conclusion and a recommendation as well to my other colleagues from other municipalities, is that as the City of Cape Town, we have initiated an integrated approach to water supply, and the water strategy speaks to that as well. And also that reducing non-revenue water is everybody's responsibility. And as a City of Cape Town now, we look at it from a bulk water point of view, from our colleagues at bulk. How are they contributing? And we are making it everybody's problem and responsibility, all the way to the customer, being educated about non-revenue and pressure management. And we also that the effectiveness of pressure management strongly relies on the skills and knowledge of the zone operators. So for us, it's become very important over the recent years that our operations teams, the guys that run the depots, the guys that turn the keys, the isolation valves, those guys are becoming more and more skilled and understand pressure management, and that we continuously monitor the impact of pressure management and also monitor leakage levels. And we also would like to, or we would like to encourage other our other colleagues to also understand that record keeping and documentation, it plays a major role in water demand management interventions, when we can record how much savings were realized, or even the economicness of an activity or of an intervention. So keeping those records as well. Data integrity is key. We've learned through this, which is why a key element of our future programs is around working on correcting the skewed data, improving our data integrity. It's also investment in maintenance. As a city of Cape Town, we have improved a lot, especially as far as pressure management is concerned, in terms of investing in the maintenance of pressure management. Our engineering and asset management unit or section has depots that actually focus on PRV servicing and such activities. And also we encourage other colleagues to also develop standard operating procedures, and also just utilize them, also review them, also have risk assessments for most of your activities. That's all from me. Thank you.
Okay, Ivy, thank you. That was wonderful. I'm sure you would have had a round of applause here if people hadn't all been muted at the moment. So that was a really thorough and interesting presentation. Now, what we're going to do now is we're going to take questions, and I would like Ivy and Unati and Neil to keep available. What I'm going to do, since Neil had so many questions thrown at him earlier, I'm going to try and concentrate the questions for the next half hour or so for Ivy and Unati. I think we'll have plenty of questions for both of them. I've been, while I've been listening with the one ear, I've been multitasking. Guys can do that as well sometimes. And I've been going through the chat log, etc., etc. And Unati, I hope I think Unati, you can put off your mute. You can come on to, that's the girl. Now, basically, it looks as though you've got a whole, gosh, there's about 30 of these. There's a whole team of supporters for you, it seems, after your presentation. You've got a whole team of people. Not quite, great job, Unati. Thanks, Unati. Well done, Unati. Oh, here's one. Oh, I see a lot of men in your photographs. This lady would like you to put more ladies in with all that equipment that you've got there. So that's a good one. Thank you, Unati. That was clear and straightforward. Nice presentation. I'll get to a question eventually, don't worry. Very practical. I like your city's approach. Well done. Well done, Cape Town. Well done, Unati. Good presentation, Unati. Well, here's a comment. I think to cover your network faster, you might need to consider employing ward-based community members to do the walk around for you. So that's a suggestion for finding leaks, etc. There was a question on leak detection for you. Let me just see. We've got it. Here we go. Okay, do you do everything or do you do anything or everything to encourage residents to report leaks in time? And then once reported, how many leaks are you fixing within your 48-hour target? That's a question for you. You can answer that one now if you want, while I go through some other ones. We're going to give you a whole barrage of questions since you didn't get a chance to answer them earlier. Everybody's got questions for you. So maybe you could answer that one, Unati. Are you doing anything to encourage the local residents to report leaks that they find in order to try and fix leaks as quick as possible?
Yes, there is an initiative through the education and awareness, making it available, letting the residents know which numbers to report to, or SMS, or which number to call. But there are obviously those who just let the leaks go and never report them. Hence, we have the leak detection team that will target each and every area so that all those leaks that are not reported can be repaired.
Okay, no, that's a good answer. And have you, this comment here about the possibility of employing ward-based community members to walk around your zones looking for leaks, etc. Is that something that the city would look at? It's obviously a job creation as well as a community involvement initiative that someone is suggesting. Is that something that the City of Cape Town would be looking at in future, perhaps?
Yeah, that's a good suggestion, because we also have the EPWP programs. So it will be best to use the community people under those programs.
Okay, no, that's
good.
Okay, that was good. We've got a comment and a question. A great presentation indeed. Have you carried out a cost benefit analysis for your, I think you mentioned that you're saving 5 megalitres a year on leaks, etc., versus the operation and maintenance costs. I think the question is comparing the savings that you're making to the cost of making those savings. Have you done that analysis? I gather from what we've just heard from Ivy that it sounds as though you keep all the information on everything. So I'm fairly sure the answer to that one is going to be yes somewhere, but maybe you'd like to comment.
Yeah, also, okay, I wanna throw that question to Ivy to give an answer on that one.
Okay, that's good. You're going to be
that's
a manager's response, which is to delegate the answer to Ivy. Okay, Ivy, your turn. You're up.
Yes.
You can put your video on.
Not...
We like to see you as well.
Oh, okay.
Neil,
yes.
You can keep yours off just now.
Okay,
oh,
we have not.
We can't see your faces.
I've got the light on again.
You've got your light on again. We can't. Yeah, that's better.
Yes. Yes, we've looked at a benefit of some sort. We don't have all the parameters to do a proper cost benefit analysis that justifies the investment that we are making into leak detection. For an example, we just recently purchased equipment of over 3 million. We do know that we saved volumes in terms of the volumes of water, in terms of the data that Unati has, but we've not done an in-depth long-term cost benefit, which is something that is now part of the plans now to refine our 10-year plan. That is also part of the work that now we are incorporating.
Okay, good. You can both keep your mutes off at the moment. No, put it back on so we can hear you, because I'm going to ask questions and you can both jump in.
Oh, okay. Okay.
So depending on who wants to answer, you can sort of shout at each other or decide. Okay, question on ground penetrating radar. Unati, I think that might be for you. I'm pointing that sorry, I'm going the wrong way. Ground penetrating radar. Are you able to pick up asbestos cement pipes with ground penetrating radar?
Yes, we are able to, as much as the GPR doesn't tell you the type of the pipe, but already there is a background work that you need to do before you use it. Already you checked what type of a pipe that is in that area, and you have your plan more or less, even because one of the reasons why you would use your GPR is because maybe the plan that you have, it's not as accurate as you see the what's happening on the ground. So yeah, we have been able to pick up those pipelines.
Okay, thank you. I've got another follow-up question. We're talking about asbestos cement pipes. Okay, yeah, I mean, you've got about 6,000 kilometers, I think, of asbestos cement pipes in Cape Town. On your plastic pipes, Stuart Hamilton in his presentation was touching on the problems of finding leaks on plastic pipes because the sound doesn't really travel that far. And even at high pressures, which your system is a high pressure system, you're not really getting more than 40 meters from the position of a leak until you can, the noise disappears. Have you experienced that? Have you got any feeling yourself for finding the leaks on the plastic pipes and how far your teams? I mean, I notice you've got some ladies there using the equipment with much better hearing. It could be that Stuart's 40 meters is just because his hearing's not up to scratch. Are you maybe getting 80 meters with your teams? Is there any, have you got any thoughts on that one?
Yes, Ronnie, when it comes to plastic pipe, yeah, it tends to be difficult to just pick up a sound just like that. Hence, we will consider doing it when it's less, when there is less demand, and also when there is less noise.
Okay, so you're doing it at night time. You do it at night time as well. Okay. I've got one for Ivy. Ivy, you indicated some figures in your slides that your non-revenue water for the city of Cape Town is currently up at around 31%. Okay, it's a double-barreled question, this one. I've been thinking up a really difficult one for you here because I think you deserve it. You've got, you're up at 31%. In Jay Bhagwan's presentation from 2016, which was before the drought hit Cape Town, you were at about 21%, okay? And my question to you is, percentages can be quite misleading when it comes to non-revenue water. And I use percentages, I'll be honest, but I often get told not to, because the problem with percentages is if you reduce your consumption, as would happen in a drought event, and you get the residents to reduce their water consumption, you can sometimes find that your percentage non-revenue water will increase despite the fact that the leakage hasn't actually changed, because the total input to the system has dropped and it hasn't come back to where it was. So in 2016, you were using an average of 1,000 megalitres a day and you had 21% non-revenue water. How much are you using a day now that is giving you this 31%? Is that maybe part of the issue?
Yes, it could be part of the issue. We are using just below 700 megaliters a day. I think I've not seen the stats for this past
That's
week,
good.
but we are between 650 minimum, and it goes up to maybe 720. So an average is around 700 megaliters a day.
Okay, that I'm just follow my logic here. If you were using, let's just say you were using 1,000 megaliters a day in 2016, and you had losses of 200. You would have had 20% losses, non-revenue water, all right?
Yes.
Now you're using 700 a day because you've managed to squeeze 300 out of the consumption, but your losses are still 200. Let's say, because the losses don't really change. I mean, your losses are still 200, but it's now 200 over 700. That would give you 30% non-revenue water. So you might be making yourself look a bit worse than you actually are. You should maybe have been getting bonuses over the last few years rather, because the number, be careful using percentages, because by achieving what you've achieved on reducing the demand, your non-revenue water has to increase.
Yes, no, you're right, Ronnie. I think that the thing is our meters, the effort is to work towards the integrity of the volume. So the system input volumes itself, it's to improve those volumes. So it may be that we are saying we actually using 1,000 megaliters a day. However, this is just meter information that's passed on from people to people, and it's old meters, so it's meter inaccuracies. And at a bulk level, if there are meter data issues, it will make a big difference on the volumes that we get from them. So we do acknowledge that we are doing a lot of programs that to address non-revenue. However, the feel in the water and sanitation department is we can do better, and also the data integrity, there's room to improve around that for us to be comfortable with what we would be considering doing good within our programs and interventions.
I mean, this is tongue in cheek. I'm not actually proposing that you do this. But if you want to get back to 21%, what you could do is bring in a big company like SAB InBev or something like that, and they'll use 300 million cubes a year, or 300 megaliters a day of water for some big factory, and you'll be back up to 1,000, and then your losses will be back down to 21. So you could do that.
They won't look bad.
Then you won't look bad at all. Okay. The second part to my question, which you never alluded to in your presentation, was you showed that you showed a graph of the savings from pressure management up at about 70 megaliters a day, and it jumps up and down a little bit, and then suddenly towards the end, in the last year or so, it suddenly dropped from 70 and it's gone back down, you said, to 20.
Yes.
Okay, I was listening to what you were saying very carefully.
Thank you.
And what you said was that you've decided to increase the critical point pressure in your zones, and that by doing that, your savings from pressure management have been wiped out to a large extent. That doesn't sound like Cape Town to me. I mean, it sounds like many other cities that I work with, but it doesn't sound like Cape Town. What is going on there? Maybe you might explain that a bit.
Yes. So basically, the 70 megaliters a day was achieved by reducing pressure all the way to 5 meters at the critical points. So we actually had people getting less than 5 meters of water, and there were periods where for an extent, but this was also supported a lot by the education. So people understood that there was no water, so we had to conserve water. So reducing water to 5 meter head at the time was reasonable. However, since then, when the restrictions were relaxed, we had to go back to the standards and norm and the guidelines. The Red Book guideline for pressure and water supply, it prescribes 24 meters at the property boundary. So we then now had to reinstate our zones to operate as per the norm, because now we're moving back towards a direction of supplying water under the normal conditions. So as part of the approach going forward after the drought, and after we sort of recovered from the drought, it was now we have to increase the pressure at the critical point from 5 meters or from 10 meters to the 24 meters that's prescribed or that's on the guideline, and also that we prescribe now on our documentation, that we're going to at least provide that minimum of 25 meters. So that played a huge role.
Okay, you didn't say that in your presentation. That was a really, you never mentioned that in your presentation. That actually ties in very nicely with a question from Zwim, who gave us a question this morning, which I didn't answer this morning, because I really didn't have an answer and I wanted you to answer it. And I think you've just answered it. He was indicating that throughout South Africa, and particularly in KwaZulu-Natal, there's a tendency when you're supplying poorer areas, and in particular black township areas is how he's phrased it in his question. He's suggesting that they are supplied at a lower standard than the affluent areas, and he questions that this is, he indicates that DWAF, Water Affairs and Sanitation have policies in place which encourage this type of behaviour. And the question is, shouldn't everybody be given a certain minimum level of standard? And I think maybe you could just allude to that. I think you've already answered it to a certain extent, and it ties in very nicely with his question.
Yes. Now, the City of Cape Town's approach has been very clear and very transparent from the beginning. Obviously, we went through a drought. We had to reduce pressures where we could and where we could realize the best benefits. So everywhere there was high minimum night flows, we had to reduce pressures. And this was irrespective of whether it's a low income area, middle income area, high income area, we reduced pressures. Actually, the City of Cape Town went to an extent where if you were consuming more than what was prescribed during that stage of the restrictions, we were installing restrictors at your property, no matter how rich you are. So we were doing that in Constantia, across board. But when the restrictions were relaxed and we moved on to the new normal, then the approach was, let's go back to the guidelines of network optimization. So the best systems operate on certain pressures. The guidelines prescribe those pressures. So the minimum pressure at the critical point, which is the point in the zone that will get the least amount of pressure, by all respects, would be 25 meters. And the guideline actually provides, I think it's 24 meters. So we said no, 25 meters to give room for that error. I do acknowledge that when the zones now are operated over time, we do find that the pressure drops to below 25 meters, which is why when we get complaints, we always have a systemed approach. The key part to being ISO certified is the system approach. So there's a process for when we receive a complaint, what does operation have to do? Because we can't just always run to the PRV to open up the system. Operations must go inside, must first check their documentation, whether did they close any valves in the recent days. They must go back to where they've gone to close valves. They must do valve verification. So they must go and open up all the internal system valves. So we kind of follow a systematic approach to sustain as much as we can. Doesn't mean we're perfect, but we do the best we can.
Okay, I think that's a great answer, and I'm not criticizing you at all, by the way. I have to say that I believe that what Cape Town did was exemplary, and I realize that you went way below the minimum level of pressure. And part of the reason for doing that was the alternative was too terrible to imagine. The alternative was that you were going to run out of water completely. And by doing what you did, you managed to make the water you had last through to the point at which you got through the day zero. You did not cut people off. And that is a message that we will be touching on tomorrow in a lot of detail. And I think it's, Cape Town got a lot of criticism that in my view, they didn't deserve, particularly in the international press. I think what Cape Town did is an example that every city should look at. And if they get into the same situation, which they will at some point in future, they should do exactly the same and be totally aggressive on reducing pressure, but keeping the system operational 24/7. Otherwise, you cut people off and then you're in big trouble. You end up with cholera, typhoid, your pipes burst, you get air in the system, sewage in your pipes. You end up in the what Neil and I experienced in India. And if anyone's got any questions about this, send them to India for a couple of weeks and see how they do it there, and then come back and they'll take your pressure down to 2 meters and just keep it pressurized. So I think it's great. I think you did a great job. Comment, I'm excited for this presentation coming from a rose amongst thorns. I think that's aimed at Neil. I think that's for Neil, that one. Or is Neil a thorn? Yeah, it could be. Neil could be the thorn there, actually. So anyway, Untati, how do you successfully make residents report in time? Any motivation? What could be causing so many bursts? Oh yeah, here's a question. I noticed, Ivy, in your presentation, you highlighted 3 areas that you seem to have a lot of bursts. Was it Durbanville, Somerset West, and Rondebosch? I think those were 3 areas that were all kind of red. And I would have thought you'd have had more bursts in the Cape Flats areas than some of, I mean, Somerset, why is Somerset West and Durbanville so prone to burst pipes and not Mitchell's Plain, Kailicha, where you're at the lowest point? So you're going to get the highest pressures there, I would have thought. What's your thoughts on that? Why are we getting so many bursts in some areas and not others? That's the question.
Okay, probably a few answers to it. Firstly, not Mitchell's Plain or the rest of the other areas, because we already have pressure management coverage in those areas. So we're already reducing pressures in those areas. They're already getting the 25 meters of pressure at the minimum, at the critical point in those areas. And then why the areas that are highlighted, when we overlapped the pipe bursts, and these are confirmed bursts, because there's also the bursts initially are triggered by complaints for repairs. Then when the team goes out to repair, they're the ones that come back and say, we actually repaired a burst, and then we document it as a burst. So it also goes through some data integrity process on its own. When we looked at that and overlapped the bursts with the pipe material, we noticed that the pipes that the bursts were occurring on the pipe material, on the AC pipes, and that the operating pressures at those pipes or in those areas were relatively high. I mean, we're talking 90 meters as a norm for them. So it did trigger for us to say we need to look into it and reprioritize going forward in terms of pressure management going forward, but also align it with pipe replacement. So I'll tell you now, Ronnie, that in Somerset West, they've already started pipe replacement in some of those areas where you see the bursts, the best stats information. And we are coming in already, like Bizweni zone, it's a big Somerset West zone. We are already coming in now with the prelim to start a design of implementing pressure management within those areas to kind of align the two programs.
Okay, wonderful. You're batting all the questions we throw at you. That's wonderful. A question here, which I'm going to answer myself. What do you mean by critical points? Someone's asked what we mean by a critical point. The critical point is a point within a zone which experiences the minimum pressure in that zone. So that's the point that we want to make sure has the specific minimum pressure, which Ivy has just mentioned has been pushed up to 24 meters in Cape Town. So in a particular zone, there may be an area which might be on a little copy or up on a little hill or something, and it only gets 24 meters of pressure. That's the point in the zone that dictates how much lower you can drive the pressure. So the critical point is the key point in a pressure zone that dictates how low we can go with the pressure. So I've answered that one. I've got a question here that says, hi, Ivy or Untate. Has the city been able to quantify the losses due to inaccurate meter readings? If so, what trend did you pick up that resulted in the meters being inaccurate? And if not, how do you plan on going about correcting the inaccuracies? That's quite a hard question, that one. So I think Ivy and Unati, I'm not going to answer that one.
I'm also not going to answer that one.
Okay, you're going to bat
but
it
that's
to
because and then that's because the meter management sits with obviously our other colleagues, and the main driver behind there was the slide where I said the key focus areas to reduce non-revenue water, where a steering committee has been established to integrate the programs. So the specific director for distribution, for water distribution, is now has now appointed a program manager for non-revenue who is collating this information from all these people that implement interventions, from all the people that implement interventions, and also to use that information to establish what the impact will be. As we are busy replacing bulk water meters, what would be the impact of that? And also the industrial meters, what would be the impact? So that is currently under it's going through a data integrity process of refining, but there are estimations that are public knowledge in terms of what we are documenting as meter inaccuracies.
Okay, that's wonderful. Good, good. I've got a question here again for you, Ivy. It's from Chabedi. I know I've known Chabedi for many years from his water affairs days. It's very formal. It's Mrs. Masela. Most municipalities do not have dedicated standalone units like the City of Cape Town's Water Demand Management Unit to deal with non-revenue water. What advice can you give in this regard? Can you also share with the municipalities the benefits of establishing such water demand management units?
We are obviously an example of those benefits, I take it. The fact that we're able to implement so many interventions that are focused on water demand management. So it only makes sense to have dedicated people at least focusing on non-revenue water interventions. But with regards to the issue of to the issue of other municipalities and what can they do, is make non-revenue water everybody's responsibility. I think we at some point water losses are left to one discipline to resolve, and we in the city now are working harder towards that integration, because even us as water demand management, we don't control everything that has to do with non-revenue water. So the important part is make everybody responsible for an element or a component of the non-revenue. What is their contribution with their program, wherever they are, that contributes to non-revenue? And then maybe the idea of having then a program driver in terms of integrating it makes it easier. But I think what I have noticed was we made more progress as the city, especially when we were forced through the drought. We made more progress when we really set and united towards non-revenue, where it was everybody's problem, including the customers. So even the education and awareness approach had to change and adjust about how we're going to educate our everyday people in the street about non-revenue water, about water losses, about pressure. That has been our approach in the city of Cape Town.
Okay, fantastic. We just for everyone's benefit, we will have a presentation tomorrow by Mr. Peter Flower, who's also from, during your crisis, he was your water and sanitation director, and you'll get a chance to ask any more questions about anything that you've heard about Cape Town. Peter should be able to answer some of these tomorrow. I've got one more question for you here, Ivy, before I let you off the hook. Thank you for a great presentation. The city's hydraulic modelers use a spatial geodatabase of the consumer billing data to populate their models. Are you using this database to carry out any top-down water balances within specific zones? Are you using your this geodatabase of the consumer billing data? Are you using that at all for a top-down water balance? That's quite a technical question for 4:30, which I apologize for, but I'm sure you can handle it.
Yes, yes. The information it comes from. So there is the hydraulic model in the city of Cape Town is connected to the SEP information. So whatever is being read on SEP is sent back to the hydraulic model. So yes, we are using that information for the water balance, and also for the zone water balance, for where we've created sub-zones or water zones. We also use the meter reading data to develop that water balance, which is still at its inception stages, because those zones are dependent on the discreteness of those zones and a whole lot of other operational challenges that we overcome on a daily basis. So it's been difficult to get a good water balance at the bottom up approach at a zonal level, but we are making headway towards that.
Okay, I've got a question for, I think this is for Unati. Unati, would you like to come off mute for a second? I see you're on mute there. Maybe pop off the mute so that you can speak to us. That's it. And put your video on. Good. The question is quite a nice, short, clear one. Out of your, they've said 34% non-revenue water. I thought it was 31%. Has it gone up? Or was it always 34%? Is it 34%? Anyway, the question is, it is 34. Sorry, I'd written down 31.
2021 is 20. Is
all right, okay, 21 to 34. Sorry, it's past my bedtime. Anyway, out of the 34%, what would you guess is of that amount? how much would you say is physical leakage?
I haven't checked the.
Okay, that's all right. I just wondered if you had a number off the top of your head, and you could just say it's half or it's a third, or any idea? No.
No, I have no idea.
All right, no worries, no worries. I thought I'd ask anyway. We're basically getting pretty close to the end of today. Unfortunately, the more questions you answer, the more I seem to get. And it's just, the numbers are just going up. And I'm worried that we might end up being here all day. So I think we're going to call, I think we should, I'll take one question for Neil, just so that he doesn't feel, because Neil's been sitting here quietly. Neil, I've got a question for you that we'll throw at you just to finish us off.
Sorry, Ronnie, just briefly, I think there's still one or two questions for Stuart also. I don't know if Stuart is still around. It's maybe way past his bedtime.
He'll be watching the Penguins by now. I've got no doubt.
Okay. But
if Stuart's around, Stuart can jump in. You can pitch a couple at Stuart. I'm going to pitch one at you.
Okay, I'm not sure if it's a recording, but we are seeing Stuart there.
All right, okay. Well, we'll bring him back in. You can ask Stuart the questions, because I've been fielding. I can only multitask two things at once. Question to Neil: can a PRV be designed based on flow as the variable rather than the outlet pressure as the variable? Can I use a flow control valve as an option for pressure reducing a gravity line? Does that make sense? Question to Neil: can a pressure reducing valve be designed based on flow rather than the outlet pressure? So what they're saying is, I think you actually mentioned that if you put a flow pilot on, then the PRV operates for flow rather than pressure. Did you not say that in your, did you not answer that? You mentioned something about that.
There was a similar question on that, and so if I understand the question correctly, is that if you would like to control the flow on that pipeline, then obviously the valve stays the same. So the control valve stays the same. The only thing that changes is the pilot valve that you put on the control valve. So if you would like to control the flow, then certainly you sort of the flow would you would use that to size that PRV, but it's probably good to have the pressure information in any case, because if you, for example, want to do a flow control on a valve, and by doing flow control, you're going to get a very big pressure reduction ratio over that valve. You may end up getting cavitation then on that valve. So it's our recommendation is get the pressure and flow data, and then sort of do the sizing on that.
Okay, no, that's fine. I mean, I'm keeping. We were supposed to finish at 4:30, but we're giving you an extra free half an hour if you need it at no additional cost at all, since this is a virtual event. So we'll give you, it's like an extra 10% on top of what you were expecting. So this is, I've got a comment from Zwem here. Oh, that was in connection with that last question. It just says, well done, ladies. Your presentations were very informative and your knowledge of the subject matter is impressive. Please keep it up. There you go. Well done, Cape Town. Neil, you didn't get anything like that, although people were quite impressed with the pressure management stuff, I must admit. So you did get some good questions. On the topic of non-revenue water, there's serious literature saying you shouldn't use percentages. As an ex-chairman of the IWA, I have to admit that that is our policy. Do not use percentages under any circumstances. Having said that, Everyone in the world still uses percentages, and it's really difficult to get away from it. Having said that, I have tried to highlight the potential danger of using percentages. And I think Cape Town is an excellent example of why they sometimes might not work as well as they could work, in light of the fact that Cape Town have done so very well, and yet their percentage non-revenue water has almost doubled. So I think Cape Town, you might want to come up with another indicator to support the percentage indicator that gives the true picture of what's really going on there, because otherwise you make yourself look bad when you're actually doing really well. So I think everyone agrees on that. Neil, do you want to ask Stuart a question quickly?
Yes, can I just check if Stuart, are you still, oh, good, thanks Stuart. So Stuart, there's a question from Corky. So, and he was asking, when is the right time to stop with leak detection? You know, from an economical point of view, within a specific zone. So basically a question around sort of the economics of leak detection.
In reality, you never stop unless you get to a stage where your burst frequency no longer happens. So if your natural rate of rise becomes 0 and your leakage becomes very, very economical, and you have no shortage of water, and your cost of water in production is incredibly low, then you may be able to start looking at not doing leak detection. But while you have pipes in the ground that we currently have in the condition we've got them and the material we've got them, it's not something that will happen in our lifetime.
Okay.
That's my personal opinion. Yeah. I've never met a leak-free system yet, no matter what people claim. And some of them claim they got incredibly low levels of leakage. They do also have very active leak detection teams out there keeping it that low. So it doesn't stay low because they're not doing work. They're staying low because they're working harder.
Okay, no, thanks, Stuart. And then
probably not the answer you wanted.
yeah, I was looking, you know, for for maybe more like a scientific sort of approach, but I think we get your comment. So
well, like I said in the presentation, the easier not to be clever, because you may end up looking stupid. So if you just be stupid, you know, just don't be clever and look at economic levels of leakage. Just be stupid and go and fix the leaks.
Okay, no, so, noted. So there was a question from Hino, and he was saying that what they are finding is that there are many companies sort of doing leak detection, and you know, maybe with varying degrees of success. I mean, how does it work in the UK? Can anyone basically say they are, you know, a leak detection company, or is there some, you know, is there some paperwork involved where you can say, you know, I've done this course, I've got that qualification, so therefore, you know, I'm now a leak detection company? Is it or any other country, you know, other than the UK?
No, we've looked at this in the IWA, and we've looked at it many times around the world. And I tried introducing something which was like a driving license operating, where you actually have a license to operate. So you want to become a leakage engineer, you need to sit a course, you need to get a certificate, you need to get a driving license. And wherever you go, you can show this driving license to say, I am a qualified at whatever level. In reality, there isn't anything. Anybody can set themselves up as a leakage engineer anywhere in the world, be it in the USA, in Australia, in the UK, in Canada, in Europe. They all do the same. Anybody can call themselves an engineer. Anybody can call themselves an expert. Any company can say they're more better advanced than the other ones. And it's all to do with trial and error and case studies, and just ask for references before you employ them, because it's a very nice earning of a quick hit revenue return to say you're an expert, because it might take 5 years to get found out. And that's the unfortunate situation we're in today. I mean, I've been doing it 40 years, and I'm still bluffing the people. So it's great. It's I just don't go anywhere. I don't go anywhere the same place twice in a few years.
Here we have you, speaking as an international speaker on leak detection. So, Stuart, and a last question from my side is, in, let's say, 20 years from now, where do you see leak detection technology? Like, what's the next really, wow technologies that you think is going to come out of leak detection, but the type that really works, not the fuzzy sort of type, the stuff that really works. But what do you think is the next, the next technology that's going to take us to the next level on leak detection?
I mean, the thing is, what we're looking for many times, and we've looked at it for years, and MIT in the US have tried it, is robots that live in the main. Little robots that will go around the main, they will hear a leak, they'll activate the leak, and they have a platelet in with them that actually fix the leak from inside the pipe as well. That's the dream that we're all going for. That is where everybody's driving for. In reality, I don't see anything moving outside the acoustic range of technologies. Satellites, if it gets adopted, will be brilliant, but we don't own the satellites. We have to use a satellite that's been put up by a third party, and we have to use their data. So in reality, I can still see us in 20 years' time using acoustics, using human intervention, and just keep going. And the sound profile of the acoustics are getting better, and the methodology of listening for leaks is changing away from acoustic sound to vibration. So that's slightly changing, but at the end of the day, I can still see the principle being where we are now, because it's where we've been since I started in 1980, and the person that trained me, he started that in 1960, and nothing has changed much. We're still, it's still going out there and hard work. And until we get the perfect pipeline, we're going to have consistent to have leaks. And as while we've still got leaks, we've got to find them. GPR, ground penetrating radar, if it becomes better, will be good. Drones will be there, but nothing has really took anybody's eye that really says, wow, that is impressive. I've not seen anything like that for a good number of years.
Okay, Stuart, thank you very much for that. If you put little robots into the pipes to search for leaks, people might not want to go to the toilet anymore. That might be anyway. On that note, I think we're getting close to the end for today. I apologize to everyone whose question has not been answered and hasn't been asked. We have tried to cover as many questions as possible. I do realize there's still 23 open. I'll ask one final question to Ivy, and this will be the last question for today, and then we'll close down and start again tomorrow morning at 9 o'clock again. Yep, 9 o'clock. The question to Ivy, it's a technical one on water balances at the reservoirs in the system. And it says, hi, Ivy, when you do your reservoir water balances, how do you plan to measure losses within the reservoirs themselves in a way that can account or pick up the possible leaks in the reservoir and or evaporation from the reservoir? I would imagine the evaporation is probably not as significant as the potential leakage from a reservoir. How are you picking up leaks in your reservoirs?
At this point, it is one of our future interventions to we are working towards being able to produce the reservoir water balances. We've got meters that meter water going into the reservoirs, and we've got reservoir outlet meters. The objective is to measure the water it's to log water going in and water going out. And we also have, we call them overflows. We also have overflows, and those, depending on the area as well, with the different regions and approach to reservoir construction or expectations from reservoirs, some of those are actually metered. So we've got our reservoirs where we've metered the inlet, we've metered the outlet, and also the overflow is metered. And those are, most of our reservoirs are actually covered. So we don't really lose much to evaporation. So it's more about leakage itself. So we just intend to be able to measure the volume of water going into the reservoir, the volume of water over or flow rate over a period of time going out of the reservoir, and also the zones, connecting that to the zones, because we've got big reservoirs that supply 5 to 10 zones. So it's 10 water zones that are discrete being supplied from one big reservoir. And the idea is to be able to have a water balance in that regard.
Okay.
So
Thank you,
we intend to use logging and metering, and just do a simple subtraction equation and work from there when there's leakage levels.
Okay, thank you for that. And I think I'd just like to say a word of thanks to everyone that presented today, to Ivy, to Unati, to Neil, to Stuart, to Jay. And I think we've been trying a new format, as you've probably gathered, where we have more time for questions and slightly less time for the presentations. And it seems as though no matter how much time we allocate to questions, we've always got more than we can answer. So I do appreciate everyone taking the time and effort to put in a question. And thank you for asking such intelligent and good questions. I think it's made it very worthwhile. And as I say, thank you to the speakers for batting them off so well. And we'll finish for today. We're quite a bit over time, and I see we've still got well over 100 people listening. So thank you for your attention. We'll see you tomorrow morning virtually at 9 o'clock. Help yourself to coffee and tea and biscuits before we start, and we'll chat tomorrow. Thank you once again, and we'll call it a day at that. Thanks for everything.